Let's explore the concept of limits through some examples. So starting with number 1, what is the limit of x squared as x approaches 2? Okay, well, we've got to think about what happens to the function x squared as x gets closer and closer to 2. What does x squared get closer and closer to? Well, it's a nice smooth and continuous function. It gets closer and closer to the value of 4. So in this particular case, the limit is the same as plugging in the value. When you have nice smooth continuous functions, they are the same. So if you can plug that number in that x is approaching, get a clear value for y, it is often going to be the same. Okay, let's look at a similar example. How about the limit of e to the x as x approaches -1? Okay, well, e to the x is a nice continuous smooth function. Recall it's about 2.71828, the number e is. And if you plug in the value -1, that's e to the -1, which is just 1 over e. And that's the answer. So it's just 1 over e. E will be one of our best friends in calculus, and we will see why later. Okay, these particular examples, the limit is not doing anything particularly interesting, but it's important to understand that it is like an equality. Now, this next example will be more interesting. So let's look at the limit as x approaches -2 of x squared plus 5x plus 6 all over x plus 2. Okay, now we can't just plug in -2. We get a 0 in the denominator, and that's, generally speaking, undefined. So what do? We can check first to see if we can do any algebraic simplification. And so anytime you have a polynomial, you can check, does it factor, and in particular, does it factor as a factor of x plus 2, right? Because that's what you're hoping to cancel. So in this particular case, we can factor this to x plus 2 times x plus 3. Okay, this is really nice now because at this point, there's a 2 there in the denominator. At this point, you've got 0 over 0, right? So you've also got a 0 in the, I'm going to put a -2 there, just x plus 2. We've got a 0 in the numerator and the denominator, but they cancel, right? And so what we end up with after the cancellation, limit as x approaches -2, it's x plus 3. And this is what you want to end up with after your simplification, a nice smooth function where you can just plug in the value and we get 1. Okay, so that's nice. Now let's take a look at what's actually going on here. Okay, so we started with this function, x squared plus 5x plus 6 over x plus 2, but it simplifies to x plus 3. Okay, this is interesting. So is it the straight line x plus 3? Well, almost. If you start with this function, -2 is not defined. So this is what you're going to end up with. You're going to end up with a graph where the graph is just x plus 3, and it's going to have a hole at -2. Okay? So there's a straight line, and it's got a hole at -2. And so what that means, the hole is where it's undefined. Okay? There's no value in this function that exists there. But a limit checks to see what happens as you get closer and closer to -2. Right? As you get closer and closer to -2, it seems pretty clear that you get closer and closer to a y value of 1. Okay, a limit, if you like, fills in a dot. Okay, a limit is for an individual point, right? You're approaching an individual point. And so you can get closer and closer and closer to that individual point. You can plug in like -1.99999999999, and you'll get really close, right? You'll get 1.0000000, all the same number of zeros with a 1 at the end. And so it's clear that you're getting closer and closer. So that's the visual of what's going on here. Let's look at some additional examples. Okay, I want to start with some functions. Okay, like let's consider the following. Let us consider, how about f of x equals 2x. Okay, so we're going to start with this function, and what we're going to do now, we're going to look at the limit as h approaches 0 of what? Of f of x plus h, excuse me, minus f of x, all over x plus h minus x. Okay, that's our definition of the limit. Denominator is just h here. Okay, I sometimes like to write it like that to reinforce that it is the slope. It's y minus y over x minus x. That gets a little bit missing from the denominator when you just have the h in. Okay, so we have a new limit to compute, and we have a function to plug in. Recall from the previous video that this is actually the definition of a derivative. Okay, so this is a different type of a problem. We're actually going to figure out from this definition what the derivative is of 2x. But it is a limit problem. So let's plug in for our functional notation. Okay, limit as h approaches 0 of, well, if it's 2x, you've got to put in 2 of x plus h minus 2x all over h. And then limit h approaches 0 of, well, we've got 2x, I'll write it out, 2x plus 2h minus 2x all over h. And you can see that the x's will cancel, the 2x's. You're going to be left with 2h over h, but then the h's cancel. So that's really exciting. You get the limit as h approaches 0 of 2. And this is kind of cool. You know, technically we haven't had one like this yet where, wait a minute, there's no h there. Well, if y is always 2, it doesn't matter what h approaches. This answer is clearly 2. Okay, so there is a functional notation example. And this is a key example because finding limits as h approaches 0 of f of x plus h minus f of x over h, which is the definition of the derivative, is something that you will get a lot of practice doing. So let us do one more like this. And we will go with number 5, last one, f of x equals x cubed. Okay, so we're going to use the same definition, limit as h approaches 0. This time I'll just write f of x plus h minus f of x all over h. Okay, so what do we do here? Well, we've got to cube it, okay? So let's just write that in first, and we get x plus h cubed minus x cubed all over h. Okay, so how do we do x plus h cubed? Recall Pascal's triangle. Pascal's triangle is basically 1, and then you've got, is it just 1, 1, and then 1, 2, 1, and then you're just adding in the middle, 1, 3, 3, 1. And what this basically tells us is if you have, you know, this is like x plus y, the first, 0th, first, second, and third power, okay? So this is for a cubic right here, this bottom line. And so the way that you would use this in a problem like this is the following. You would say, okay, I've got 1x cubed, and then I've got 3 of, these are the coefficients, the next term. Well, what's the next term? You go down in x's and up in h's. So it's x squared h plus another 3. 3 down in x's, up in h's, and then finally the 1h cubed. Okay, so that is our x plus h. We've also got this minus x cubed. I'll put it up top, all over the value of h. Okay, so what does this simplify to? Okay, the x's cancel and we're left with the x cubes. We're left with the following. We've got 3x squared h plus 3xh squared plus h cubed all over h. And what we can do next is we can cancel out the h, okay, which is what we want, because when it's just h is numerator and denominator, it's 0 over 0, we haven't made progress. But now we're going to get 3x squared plus 3x h squared plus, that should be a squared. And then plus h cubed. No, because we're factoring out 1, sorry. Change. This will be 3xh plus 3xh squared. And finally at the end here, we can now plug in h is 0. And so we're left with, this is going to equal 3x squared. And what we have discovered is that 3x squared is the derivative of x cubed. Okay, so these are a sample of limit problems, and I hope you have fun with them.